Have you ever felt something meant to be your greatest achievement turn into a nightmare? When what should have elevated you to the top relentlessly pulls you down? Imagine 1943, Supermarine Aviation Works in Southampton. The legendary Spitfire fighter had just received a new Rolls-Royce Griffin engine, and instead of the anticipated triumph, the aircraft transformed into an uncontrollable beast. Nearly 2,000 horsepower of pure, untamed fury twisted the machine like a cork in a bottle, forcing pilots to wrestle with the controls just to keep it on a straight trajectory. It seemed every British engineer understood. The solution had to be simple, proven, reliable. But Joseph Smith had a completely different idea. His proposal met only skepticism. 2 propellers, rotating in opposite directions on a single shaft. His own colleagues called it madness, a mechanical nightmare, too heavy, too complex, too fragile for combat conditions. The Ministry of Aircraft Production wanted nothing to do with Smith's contraption. But when the first modified Spitfire lifted off the runway and accelerated to 756 kilometers per hour without a single wobble, when test pilots reported such smooth handling that one could thread a needle in a dogfight, suddenly everyone wanted to know how the engineer's foolish idea became the Allies' deadliest secret. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to tell us in the comments where you're watching from. Autumn rain in 1943 drummed on the roof of the Supermarine Aviation Works hangar, each drop marking time Britain couldn't afford to lose. Inside, under the harsh glare of industrial lamps, mechanics feverishly worked around the sleek fuselage of what was meant to be the Royal Air Force's most formidable weapon. The Spitfire Mark 21 embodied everything the Allies needed: speed, firepower, and the legendary maneuverability that had saved Britain during the darkest days of the Blitz. But something had gone catastrophically wrong. Squadron leader James McKinnon climbed out of the cockpit, his flight suit soaked with sweat despite the October chill. His hands trembled slightly as he removed his leather gloves, not from fear, but from the sheer physical exhaustion of wrestling 2,000 horsepower of barely controlled fury across the Hampshire skies. The new Rolls-Royce Griffin engine had turned his beloved Spitfire into something more akin to riding an unbroken horse than flying an aircraft. "How bad is it?" asked Chief Engineer Malcolm Whitfield, already reading the answer on McKinnon's face. "At 560 kilometers per hour, it wants to roll left so badly I nearly put it into a spin," McKinnon replied, his Scottish accent thick with frustration. "The torque from that bloody massive engine, it's like the prop is trying to tear the nose off the fuselage. Above 640 kilometers per hour, forget it. No pilot in the world could hold it straight in a combat situation." The numbers painted a grim picture. The Griffin 65 engine produced 1,850 horsepower at sea level, nearly double that of the original Merlin engine fitted to earlier Spitfire variants. This untamed power was meant to propel the aircraft to over 756 kilometers per hour, making it faster than any German fighter in the sky. Instead, the massive reactive torque, an equal and opposite force described by Newton centuries ago, twisted the entire airframe with such ferocity that pilots couldn't maintain level flight at combat speeds. Whitfield ran his hand over the propeller hub, feeling the faint vibration that never quite ceased. Even with the engine off, The engineering challenge was brutally simple in concept, yet incredibly complex in execution. Every rotation of that massive four-bladed propeller generated a rotational force that tried to spin the aircraft in the opposite direction. At low speeds, pilots could compensate with rudder input and sheer physical strength. But as airspeed increased, aerodynamic forces exponentially magnified the problem. The result was an aircraft that became more dangerous to control the faster it flew, which was the exact opposite of combat requirements. The Germans have the same issue with their powerful fighters, Whitfield said, though his tone offered little comfort. Their Focke-Wulf 190 series suffers from similar torque problems, but they've learned to work around it with pilot training and tactical limitations. McKinnon shook his head sharply. We can't outrun physics, Malcolm. This isn't a matter of flying technique or training protocols. At the speeds we need to achieve air superiority over Western Europe, this aircraft is simply unflyable. And if we can't fix this... He didn't need to finish the sentence. Everyone in that hangar understood what was at stake. The Ministry of Aircraft Production had already invested millions of pounds sterling into the Griffin engine's development and the Spitfire airframe's redesign to accommodate its increased size and weight. Production schedules demanded hundreds of these aircraft begin rolling off assembly lines within months. The Royal Navy desperately needed a naval variant, the Seafire, to match the performance of American carrier-borne fighters in the Pacific theater. Failure wasn't just an engineering snag. It represented a potentially catastrophic gap in Allied air power at the most critical stage of the war. 15 miles away, in the cluttered office of Rotoll Airscrews Limited, Joseph Smith sat surrounded by technical drawings, slide rules, and empty teacups. The chief designer had spent the last week poring over flight test data for the troubled Spitfire, searching for a solution that, in his colleague's view, increasingly didn't exist. All traditional approaches had failed. Increasing rudder size added weight and drag without addressing the fundamental issue. Modifying engine mounts to reduce torque transfer weakened the airframe structure. Adjusting propeller blade angles offered only marginal help, but created new problems with efficiency and vibration. Smith's reputation in the aviation industry was complex. At 42, he possessed an intuitive grasp of aerodynamics bordering on genius, yet his solutions often struck more conservative engineers as overly complex or impractical. He had designed propeller systems for Rolls-Royce that pushed the boundaries of what manufacturing technology could achieve, earning grudging respect for their performance and equally vocal criticism for their production challenges. His colleagues at Rotoll had learned to expect the unexpected from Smith, though few were prepared for what he proposed that gray October afternoon. Have you ever felt your brilliant, world-changing idea hit a wall of total incomprehension? Well, that's precisely how one ingenious engineer felt when he presented a solution that could change the course of World War II. Have you always been told that excess power is a problem to be suppressed, tamed, nullified? But what if I told you that very force could not only be harnessed, but made to work for you, doubling power and efficiency where others saw only insurmountable obstacles? In this video, we'll delve into the astonishing story of one of the boldest engineering solutions born in the throes of war. Initially met with fierce opposition, then recognized as a breakthrough. Prepare to discover how even the most incredible visions break through skepticism and resistance. In the autumn of 1943, against a backdrop of grim news from the front lines, engineer Smith proposed a concept that defied conventional wisdom. Instead of viewing torque as an undesirable phenomenon to be suppressed, he saw it as a fundamental force that could be harnessed. His idea was not to fight the colossal rotational energy of the Griffin engine, but to tame it using a contra-rotating propeller system. Two propellers, mounted on a single shaft but rotating in opposite directions, were intended to mutually cancel out torque reaction while providing unprecedented thrust efficiency. However, the engineering challenges facing this concept were truly colossal. The system required the creation of an extremely complex gearbox capable of driving both propellers from a single engine output shaft. This inevitably added weight and mechanical complexity to an aircraft already at the limits of its structural capabilities. The contra-rotating propellers needed perfect balancing to prevent catastrophic vibrations, and the entire assembly had to withstand the immense stresses of combat maneuvering. Most critically, reliability was paramount. The system had to be suitable for mass production and field maintenance under wartime conditions. When Smith first presented his drawings to the Rotol engineering team, the reaction was immediate and overwhelmingly negative. Senior engineer Robert Morrison called it a mechanical Rube Goldberg machine that would be impossible to produce in the required quantities. Production manager Charles Henley worried about the added weight and maintenance requirements. Test engineer David Clark doubted the system could withstand the stresses of carrier operations for the Naval Seafire version. It's simply too complex, Morrison argued during a heated meeting in Smith's office. We're talking about essentially building two complete propeller systems and somehow making them work perfectly together. The gearing alone would demand manufacturing precision we barely achieve in peacetime, let alone under the pressures of wartime production. We've only just begun to unravel this captivating story. Stay with us and watch until the end to discover how this clash of genius and skepticism ultimately played out. Your likes and subscriptions are greatly appreciated, and please tell us in the comments where you're watching from. We're very keen to know our audience's geography. But Smith, armed with his calculations, was unyielding. Yes, the contra-rotating system would indeed be heavier than a conventional single-propeller variant by about 200 pounds. However, the complete elimination of torque reaction would allow the aircraft to achieve its full speed potential. More importantly, the improved propeller efficiency would increase thrust by nearly 15%, more than compensating for the additional weight. The Spitfire Mark 21 could finally become the 470-mile-per-hour interceptor the Royal Air Force so desperately needed. As autumn turned to winter, the debates surrounding Smith's foolish propeller design were poised to determine not only the fate of Britain's most famous fighter, but also the balance of air superiority over the battlefields of Europe and the Pacific. And so, with all arguments seemingly exhausted and the project's fate hanging by a thread, Smith faced an even graver test. The Ministry of Aircraft Production's boardroom in London, on November 15, 1943, resembled a tribunal more than an engineering conference. Seated around the mahogany table were the highest-ranking officials in British aviation, their faces etched with the grim reality of a war that had already consumed 4 years and showed no signs of abating. Air Marshal Sir Wilfrid Freeman presided over the meeting with the grim efficiency of a man who had too often seen promising aviation projects fail at the most crucial moment. The story is just getting started, and there are many more astonishing details to come. Don't switch off. Watch this video all the way through. We guarantee you won't regret it. Your likes and subscriptions are the best reward for us. And of course, don't forget to tell us in the comments which city or country you're watching from. Mr. Smith, Freeman began, his voice imbued with the polished authority of the Royal Air Force. We have reviewed your proposal for this contra-rotating propeller system. I must say the initial reaction from our technical staff has been highly skeptical. He gestured to a stack of reports that seemed to dwarf Smith's modest folder of blueprints. The consensus, it seems, is that your design introduces unnecessary complexity at a time when we need proven, reliable solutions. Smith had anticipated this resistance, but the formal setting made his throat tighten with nervous tension. These men controlled the destiny of British aviation, and their decision would determine whether his months of calculations and sleepless nights held any significance beyond academic exercise. But Smith was ready for a fight, for he knew his idea was not merely a collection of components, but a fundamental solution to a problem preventing powerful engines from reaching their full potential. Sir, with all due respect, I believe it is the very complexity of the system that makes it effective. We are not simply adding components. We are fundamentally addressing the torque problem that rendered the Griffin engine unusable at combat speeds. His words were firm, despite his internal apprehension. The Director of Technical Development, Sir Roy Fedden, leaned forward, his reputation as one of Britain's foremost engine designers, lending weight to his skepticism. Mr. Smith, your proposal demands a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft. We're talking about contra-rotating shafts, a planetary gearbox, and precision synchronization that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons. The figures Smith had prepared told a very different story, but he understood that raw data alone wouldn't be enough to overcome institutional inertia. He had to convince them not just of mechanical feasibility, but of strategic necessity. The gearbox's complexity is manageable with proper manufacturing tolerances. De Havilland has already proven that complex propeller systems can be mass-produced with their variable pitch mechanisms. Our system will employ a two-stage planetary gear train with a ratio of 0, 77.1 for the front propeller, and 0, 62.1 for the rear. The differential rotational speeds will be precisely calculated to compensate for torque while maximizing thrust efficiency. Group Captain Peter Thornton, representing operational requirements, leafed through a folder of combat reports from the Mediterranean and Pacific theaters. Even if your system works mechanically, Mr. Smith, we are concerned about weight and balance. The Mark 21 is already heavier than previous Spitfire variants. Adding 200 pounds of additional propeller equipment could affect performance in ways we don't fully understand. Smith had anticipated this objection and pulled out his most meticulously prepared calculations, knowing this was the key to convincing them. The additional weight, sir, is real, but the performance gains more than compensate for it. Our estimates show a 15% increase in thrust, combined with the complete elimination of torque reaction. The aircraft will not only achieve its projected speed of 470 miles per hour, but also maintain controllable flight characteristics across its entire speed envelope. Current test flights indicate the Mark 21 becomes increasingly dangerous above 350 miles per hour. Our system will significantly extend safe operation beyond 400 miles per hour, turning it into an uncompromising weapon. Do you think you know what speed truly is? Imagine a world where every flight is a battle for survival, where the enemy is one step ahead, and you're desperately searching for a way to catch up. What if I told you the solution was found in the most unexpected place, in a system that seemed like madness, but changed the course of history? You've probably faced that feeling when everything seems to go wrong, when efforts yield no results, and competitors are gaining on you. That's precisely the situation our protagonists found themselves in. They faced a problem demanding radical measures, and what they came up with would astound you. We've often talked about the importance of not just solving problems, but anticipating them. Today, we'll show you how one bold decision revolutionized the perception of aviation possibilities. This video tells the story of how engineers, facing the impossible, created a system that allowed aircraft to fly faster than 400 miles per hour. And here's the first step towards that. You make this mistake in every project, but you don't notice it. Forget everything you've been taught about traditional solutions. It's a lie. Stay with us and watch until the end. Your likes and subscriptions are greatly appreciated. And of course, tell us in the comments where you're from. In those times, when air supremacy was at stake, and every component, every screw could determine the outcome of the war, Engineer Smith proposed something that would only baffle any skeptic. He spoke of a system capable of boosting a fighter's speed far beyond 400 miles per hour. However, Smith omitted the intense pressure exerted by intelligence reports. Ultra-intercept data unequivocally indicated that Messerschmitt was actively developing high-speed versions of its Me-262 jet fighter, while Focke-Wulf continued to refine the TA-152 series for high-altitude flight. The Allies needed every possible advantage in speed and maneuverability to maintain air superiority over Western Europe during the impending invasion. Freeman meticulously reviewed his notes, clearly weighing the technical risks against operational necessity. Your proposal will require significant changes to existing production lines. How long will it take to develop a working prototype if we approve the project? He asked, his voice strained. 6 weeks for initial gearbox design and manufacture, sir. Another 4 weeks for propeller fabrication and balancing. We could have a test rig ready for flight trials by early February, Smith replied, his confidence masking colossal technical difficulties. The contra-rotating propeller system demanded high-precision engineering that pushed British manufacturing capabilities to their limits. Each propeller had to be individually balanced to tolerances measured in fractions of an ounce, while the gearbox required gear-cutting precision normally reserved for naval chronometers. The room fell silent as the officials processed the timeline. 6 months had passed since the first problematic flight trials of the Griffin-engined Mark 21, and pressure from operational squadrons was mounting. Pilots were demanding aircraft that could match or exceed German fighter performance, especially at high altitudes where the Griffin engine's advantage was meant to be decisive. Air Commodore Ralph Sorley, who had overseen fighter development throughout the Battle of Britain, finally broke the silence. Mr. Smith, your reputation suggests that when you propose something so unconventional, it warrants serious consideration. But I must ask directly, are you absolutely certain this system will work? We cannot afford another failed modification program. Smith met Sorley's gaze directly. Sir, I'm staking my career on it. The physics are sound, the engineering is achievable, and the performance boost is precisely what the Royal Air Force needs. A Spitfire. Mark 21, with contra-rotating propellers, will be the fastest and most maneuverable fighter in the world. The bold claim hung in the air like a challenge. Freeman exchanged glances with his colleagues, acknowledging that Smith's confidence carried the weight of genuine technical expertise. This was the man who had designed propeller systems for some of Britain's most successful aircraft, and his track record suggested his unconventional solutions often succeeded where traditional approaches failed. "Very well," Freeman finally said. "We will authorize a limited development program, one prototype installation, full flight trials, and a comprehensive performance evaluation. But understand, Mr. Smith, if this system fails, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career." As Smith gathered his papers and prepared to leave, he felt the weight of responsibility settle on his shoulders like a lead blanket. The next few months would determine whether his foolish design would revolutionize fighter aviation or become another cautionary tale about the perils of engineering hubris. Either way, the legacy of the Spitfire, and perhaps the outcome of the air battles over Europe, now hinged on gears, shafts, and propellers turning in directions that defied all conventional notions of aircraft design. War would not wait for perfection, but it might well reward the radical thinking that turned impossible ideas into battlefield reality. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know where you're watching from in the comments. The morning of February 23rd, 1944, dawned gray and wind-swept over Salisbury Plain, with gusts reaching 25 knots at the experimental airfield in Boscombe Down. Inside Hangar 7, a modified Spitfire Mark 21 sat like a mechanical alien among its conventional brethren. A massive contra-rotating propeller system dominated its nose with an almost predatory appearance. The dual propellers, each 11 feet in diameter, created a visual illusion that seemed to defy the fundamental laws of aeronautical engineering. Test pilot squadron leader Geoffrey Wellham approached the aircraft with the focused attention of a man who understood he was about to risk his life for an unproven theory. At 24, Wellham had already survived 3 years of combat flying over Britain, France, and Malta, logging nearly 800 hours in various Spitfire modifications. His reputation for precise aircraft evaluation had earned him assignments to the most experimental programs, but nothing in his experience had prepared him for the mechanical complexity now affixed to the nose of Spitfire serial number RK98. The contra-rotating propeller system represented 6 months of intensive engineering by Smith's team at Rittal. The front propeller rotated clockwise at 1825 RPM, while the rear propeller rotated counterclockwise at 1475 RPM. Between them lay a 193-pound gearbox, manufactured to tolerances typically reserved for precision clockwork. Every component had been balanced to within half an ounce, yet the entire assembly still vibrated with a frequency that seemed to pulse through the airframe like a mechanical heartbeat. Chief Test Engineer Michael Lutko oversaw the pre-flight checks with a nervous energy that infected everyone in the hangar. Gearbox temperature remained within limits during ground run-up, he reported to Wellham, consulting a clipboard full of data sheets. Oil pressure maintained 60 psi throughout the power range. But Geoffrey, we're still seeing harmonic vibrations at 1800 engine RPM that we can't fully explain. Have you ever felt like you're on the verge of a breakthrough, having poured years of your life and every ounce of your energy into it, only for something unseen, unexplainable, to threaten to bring it all crashing down overnight? As if fate itself is testing your resolve. This is the feeling that grips those who dare to change the world, who challenge the conventional. Today, we'll tell a story that will make you rethink your perceptions of what's possible. A story of a monumental engineering solution that was meant to be a triumph, but nearly ended in disaster. You'll discover how even the most brilliant minds can encounter unpredictable challenges, and why sometimes unimaginable complexity hides behind apparent simplicity. In the hangar, where an atmosphere of tense anticipation reigned, Chief Designer Smith, his face betraying sleepless nights, meticulously watched every movement. Beside him, Pilot Wellham, a legendary figure whose hands knew every curve of a fighter plane, nodded, running his palm over the massive hub of the propeller assembly. This system, with its intricate mechanics, seemed incredibly complex compared to the familiar elegance of conventional single-propeller setups. The question hanging in the air was simple, yet its implications were enormous. What's our test plan? Litko, one of the lead engineers, responded with an imperturbable calm dictated by his thorough knowledge of the subject. We've opted for a cautious approach, climb to 8,000 feet, level flight at various power settings, then a gradual increase in speed up to 400 miles per hour, provided, of course, that the aircraft's handling remains within limits. We're particularly interested in torque reaction characteristics and any unusual flying qualities. Smith, standing by the aircraft's wing, appeared outwardly calm, but inside, a storm of anxiety had raged for the past week. This morning represented the culmination of his professional life, but it also held the potential for catastrophic failure, capable of destroying not only his reputation, but also Wellham's life. Every calculation had been checked and rechecked, every component tested to its breaking point. And yet, aircraft design remained as much an art as a science. Stay with us and watch this incredible narrative until the very end, so you don't miss a single detail. We'd be especially grateful for your like and subscription, as it helps us create more content like this. And, of course, don't forget to tell us where you're watching from in the comments. We're very interested to know our audience's geography. Precisely at 9:15 a.m., Wellham took his seat in the familiar Spitfire cockpit, though the instrument panel was now peppered with additional gauges designed to monitor the complex propeller system: engine oil temperature, gearbox oil pressure, front propeller pitch, rear propeller pitch. Each of these parameters demanded unceasing attention during what should have been a routine flight operation. The Rolls-Royce Griffin engine roared to life with its characteristic deep rumble, but the sound immediately transformed thanks to the coaxial propellers, becoming something entirely new. Instead of the familiar rhythmic pulse of a single propeller, the twin units created a complex harmonic that seemed to penetrate every bone of the pilot. Friends, don't switch off. Stay with us and watch this captivating story to the end. Your like and subscription will be the best reward for our work, and a comment with your city or country will help us connect even more with you. At 9:32 a.m., ground control gave Wellham clearance for takeoff, and he cautiously increased thrust. The Spitfire began its roll with surprising smoothness as the coaxial propellers completely eliminated the familiar tendency to yaw left, which every Spitfire pilot had learned to counteract with right rudder for years. For the first time in many months of testing, the Mark 21 tracked perfectly down the runway center line, without constant pilot correction. Liftoff occurred at 85 miles per hour, exactly as predicted. But Wellham immediately noticed something was amiss. The aircraft felt sluggish during the climb, requiring more power than anticipated to maintain an acceptable rate of ascent. The additional weight of the propeller system was clearly impacting flight performance far more significantly than Smith's calculations had suggested. By the time Wellham reached 5,000 feet, he was using almost full thrust to maintain a climb rate of 2,000 feet per minute, a performance that should have been easily achievable at 75% power. Tension mounted, and Wellham, recognizing the criticality of the situation, radioed, "Boscombe Control, this is Test 27 Wellham. I'm observing higher than expected power requirements for a normal climb. Requesting permission to level off at 6,000 feet for handling assessment." The response was immediate, crackling through his headset. "Test 27, you are cleared for level flight. How is she handling?" Wellham reduced power to cruising settings and was astonished by the aircraft's response. Despite the climb issues, the Spitfire felt remarkably stable in level flight. The elimination of torque reaction had altered the aircraft's handling characteristics in a way that went far beyond simple directional control. The entire airframe seemed more solid, more predictable, as if the coaxial propellers had somehow tamed the wild energy of the Griffin engine. At 300 miles per hour, the aircraft, which previously tended to roll uncontrollably, now flew with the steady precision of a much smaller, less powerful fighter. Wellham experimented with gentle turns, steep banks, and rapid changes of direction, finding that the Mark 21 responded with a maneuverability that seemed impossible for such a large and heavy aircraft. The removal of torque reaction had restored the legendary Spitfire handling that made the type famous during the Battle of Britain. However, as Wellham increased thrust to maximum, the aircraft's characteristics became truly alarming. Instead of smoothly accelerating towards its theoretical top speed, the Spitfire began to vibrate with increasing intensity. At 370 miles per hour, the entire airframe shook so violently that Wellham could barely read his instruments. The coaxial propellers, designed to operate in perfect harmony, seemed to be creating destructive interference patterns that threatened to tear the aircraft apart. "Boscombe Control, Test 27 is experiencing severe vibration above 370 miles per hour, Wellham reported, his voice strained with concentration as he reduced power to bring the shaking under control. "I am returning to base for an emergency landing." The approach to landing revealed yet another unexpected characteristic of the modified aircraft. When power was reduced to idle, the Spitfire descended much faster than usual, requiring constant throttle adjustments to maintain the correct glide path. The added weight and altered aerodynamic characteristics of the coaxial propeller system had fundamentally changed the aircraft's flight performance in a way Smith's team had not fully anticipated. Wellham landed at Boscombe Down Airfield after 43 minutes of flight testing, his face grim with the realization that Smith's revolutionary design had failed its first, most crucial test. The coaxial propellers performed as advertised in eliminating torque reaction, but they introduced new problems that could prove even more dangerous than the original difficulties with the Griffin engine. As ground crews inspected the aircraft, checking for structural damage from the severe vibrations, Smith approached Wellham with the look of a man watching his life's work crumble. The test pilot's report would determine whether the coaxial propeller project would continue or join the long list of promising aviation innovations that never survived their first encounter with reality. An emergency meeting convened in Hangar 7, 2 hours after Wellham's landing. Smith sat opposite a circle of engineers, test pilots, and ministry officials, their expressions ranging from disappointment to barely concealed anger. The modified Spitfire stood silently behind them, its coaxial propellers now still radiating an aura of mechanical menace. Air Commodore Sorley had arrived from London immediately after receiving the preliminary report, and his presence transformed what should have been a technical briefing into something resembling a court-martial. Have you ever felt your most ingenious idea, the fruit of months of painstaking labor, about to collapse due to one seemingly minor yet critical detail? How solving one complex puzzle can unexpectedly give rise to an even more dangerous one. This was precisely the acute dilemma faced by a talented engineer whose invention was meant to revolutionize aviation, but instead brought him to the brink of professional ruin in a setting more akin to a court-martial than a typical design meeting. At the center of this tense session, held under the watchful eyes of leadership, stood Squadron Leader Wellham. His flight suit still bore traces of sweat from the grueling struggle with an aircraft that had nearly torn itself apart in the sky. Sorley, his voice imbued with cold official authority, began, "Squadron Leader Wellham, please provide us with your full analysis of this aircraft's flight characteristics following today's test flight." Wellham stood at attention. "Sir, the contra-rotating propellers completely neutralized torque reaction during both takeoff and low-speed flight. The aircraft tracked perfectly straight down the runway, requiring no rudder correction, and its handling at speeds below 480 kilometers per hour was simply outstanding. Perhaps the best I've ever experienced on any Spitfire variant." A quiet murmur of astonishment rippled through the assembled engineers. Despite the flight's startling conclusion, Wellham's initial assessment confirmed that Smith's basic concept had successfully solved the Griffin engine's main problem. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to tell us where you're watching this video from in the comments. However, Wellham continued, his tone noticeably grimmer, at speeds above 595 kilometers per hour, the aircraft was subjected to brutal vibrations that made any further speed increase unthinkable. The entire airframe shook so violently that I seriously feared structural failure. Furthermore, climb performance was significantly degraded. We required almost full power to achieve a rate of climb that should have been possible at 75% thrust. Smith felt the weight of failure settle on his shoulders like a lead blanket. 6 months of meticulous calculations, precision manufacturing, and an impeccable professional reputation had led to an apparatus that worked superbly at low speeds, but became utterly uncontrollable, precisely when maximum performance was required. The irony was biting. He had solved the torque problem only to generate vibrational complexities that posed a potentially even greater threat than the initial difficulties. Chief Engineer Litko consulted his clipboard full of technical data. desperately searching for explanations that might salvage something from today's fiasco. Our static ground tests showed resonant oscillations at certain engine RPMs, but nothing approaching the intensity Squadron Leader Wellham experienced in flight. It appears that aerodynamic loads at high speeds are provoking resonances in the propeller system that we completely failed to anticipate. Director Fedden leaned forward, his impeccable reputation for technical precision making his questions particularly sharp. Mr. Smith, your initial calculations presumably accounted for the aerodynamic forces acting on the propeller units. How do you explain this discrepancy between predicted and actual performance? Smith had spent the last 2 hours analyzing precisely this question, and his answer exposed a key problem in wartime aeronautical engineering. Sir, our calculations were based on static ground tests and wind tunnel data. However, the interaction of two contra-rotating propellers in actual flight conditions, especially at high speeds, creates aerodynamic phenomena that are extremely difficult to predict without actual flight testing. The tip vortices, it appears, are forming destructive interference patterns that did not manifest in our laboratory work. This explanation was technically flawless, but it offered little comfort to officials who had invested months and significant resources in Smith's experimental development. Air Commodore Sorley's expression clearly indicated that he was already weighing the political consequences of yet another failed aircraft modification program. The question now, Sorley stated grimly, is whether these problems can be resolved within a reasonable time frame, or if we should abandon this approach entirely and focus on traditional methods for addressing the Griffin's torquey issues. Smith felt his career hanging by a thread, but his engineering instincts wouldn't allow him to accept defeat without exploring every possible alternative. Sir, I am convinced that the vibrational problems are correctable through modifications to the propeller blade design and gearbox synchronization. The basic concept remains viable. We simply need to eliminate the aerodynamic interference causing this destructive resonance. Test pilot Wellham, despite having risked his life during the morning flight, unexpectedly came to Smith's defense. With all due respect, sir, the aircraft's handling at speeds below 595 km/h was astonishing. If Mr. Smith can solve the high-speed vibration problem, we will have an aircraft that combines the power of the Griffin with flight characteristics superior to any fighter currently in service. Silence fell over the room as officials weighed the conflicting demands of technical perfection against operational necessity. Allied intelligence reports indicated that German aircraft manufacturers were rapidly developing new, highly efficient fighters. Meanwhile, the invasion of Western Europe, still months away, already consumed vast planning resources and demanded absolute air superiority over the battlefield. Smith seized this moment of uncertainty to present his plan of action. Vibration analysis indicates that the problem lies in the relationship between propeller blade angles and rotational speeds. By altering the gear ratios to adjust the speed differential between the front and rear propellers, we can shift the harmonic frequencies away from critical resonance points. Additionally, modifying the blade twist distribution should reduce tip-vortex interaction. Lithgow looked up from his calculations with cautious optimism. The modifications Mr. Smith described will require approximately 3 weeks of machine shop work and another week for rebalancing the entire system. We could have the aircraft ready for a second phase of testing by mid-March. Air Commodore Sorley checked his pocket watch, clearly weighing the timeline against competing priorities. The Ministry of Aircraft Production was under immense pressure to deliver combat-ready aircraft, and every week spent on experimental modifications delayed the deployment of squadrons that might be desperately needed over Europe. "Mr. Smith," Sorley finally stated, "you have one more opportunity to prove the viability of your system, but understand that this represents the absolute limit of our patience for experimental approaches. Should the second test flight not demonstrate clear improvements, we will entirely abandon the contra-rotating propeller program and concentrate our resources on conventional torque reduction methods." How many times have you faced a situation where your boldest idea seemed destined for failure? Imagine pouring your heart into a project meant to be a breakthrough, only for it to nearly end in disaster. Sound familiar? That's exactly how one of the greatest engineers of his time felt when his revolutionary development, intended to change the course of the war, collided with harsh reality. Today, we'll tell you how he not only persevered, but achieved the impossible, transforming what seemed like a failure into a triumph of engineering. Do you think aviation history is just a series of obvious successes? Well, get ready to discover how the most ingenious ideas are born from the ashes of near-total collapse, and how what was considered impossible became reality thanks to one seemingly minor yet absolutely ground-breaking modification. Before we delve deeper into this incredible story, stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching us from. After the meeting concluded, Smith remained alone in the hangar. His gaze was fixed on the silent Spitfire, which simultaneously embodied his greatest technical achievement and his most humbling professional defeat. The aircraft looked deceptively ordinary, its revolutionary propeller system appearing to be just another piece of machinery awaiting refinement. However, Smith's engineering eye already clearly saw the necessary changes that could transform his partially successful experiment into the very weapon of victory he had originally envisioned. The next 3 weeks would determine whether Joseph Smith's idea would become a revolution in fighter aviation or turn into a cautionary tale about the dangers of challenging conventional norms during wartime. Either way, the fate of Britain's most famous fighter now depended on gear ratios, blade angles, and the complex physics of rotating propellers that most pilots didn't even bother to understand. In the deepening twilight of the February evening, Smith began sketching the modifications that would either vindicate his radical thinking or forever end his career in the aviation industry. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching us from. The morning of March 18, 1944, brought clear skies and calm winds to Boscombe Down, conditions that seemed almost too perfect for what everyone understood to be the final trial of Smith's controversial propeller system. 3 weeks of intensive refinements had transformed the contra-rotating unit into something that looked barely perceptibly different from its original configuration, though the changes were invisible to those not intimately familiar with propeller blade geometry and gearbox ratios. Smith had spent sleepless nights recalculating every aspect of the system. particular attention was paid to the harmonic frequencies that had nearly torn the aircraft apart during its first flight test. The solution involved altering the rotational speed ratio of the two propellers, from the original 1825 and 1475 revolutions per minute to a new configuration of 1700 and 1500 RPM respectively. The closer speed differential would shift critical resonance frequencies outside the aircraft's normal operating range while preserving the torque-canceling effect that made the system so valuable. Additionally, Smith's team modified the blade twist distribution on both propellers, reducing the aggressive angle changes near the tips that contributed to vortex formation. Each blade now featured a smoother transition from root to tip, designed to minimize the aerodynamic interference that had caused destructive vibrations at high speed. The modifications required hand finishing each blade to tolerances measured in thousandths of an inch, a task that took 2 weeks of meticulous craftsmanship. Squadron Leader Wellman approached the modified Spitfire with a cautious optimism, tempered by vivid memories of the brutal end to his previous flight. From a distance, the aircraft looked identical, but closer inspection revealed subtle changes that could transform it from a dangerous experiment into a revolutionary weapon. The propeller blades caught the morning light differently, the revised geometry casting shadow patterns that seemed somehow more purposeful than the original configuration. The gearbox modifications passed ground tests perfectly, reported Chief Engineer Lithgow, though his voice carried the tension of a man who knew. Ground tests meant nothing until validated in actual flight conditions. We maintained stable operation across the entire power range without the harmonic vibrations that plagued the original system. Oil temperatures remained within limits, and the new gear ratios eliminated the resonant frequencies we identified in the failure analysis. Air Commodore Sorley had returned from London specifically to witness this second test, bringing with him a sense of institutional finality that impacted everyone present. The Ministry of Aircraft Production could not afford to endlessly pursue experimental programs, especially when conventional aircraft were desperately needed for the anticipated invasion of Europe. This flight would determine not only the fate of Smith's propeller system, but also the potential future development of British fighter aircraft. Precisely at 10:15 a.m., Wellman started the Rolls-Royce Griffin engine and immediately noticed differences from the previous test. The sound was subtly different, still the complex harmony created by the contra-rotating propellers, but somehow more controlled, less aggressive in its mechanical resonance. Engine instruments showed normal readings as he advanced the power for taxiing, and the aircraft tracked straight without the slight vibration that had characterized the original system, even during ground operations. The takeoff at 10:28 a.m. revealed the most dramatic improvement. Where the previous flight had required nearly full thrust to achieve an acceptable rate of climb, the modified aircraft now gained 2,000 feet per minute using only 80% power. The revised propeller geometry had seemingly eliminated much of the aerodynamic inefficiency that plagued the original design, allowing the full power of the Griffin engine to translate into actual aircraft performance. Boscombe control, test 27 climbing, through 8,000 feet, Wellman radioed, a cautious excitement in his voice. Rate of climb significantly improved over previous test. Handling characteristics remain excellent. Requesting clearance for speed envelope check. The reply came back immediately. Test 27. You are cleared for speed trials. exercise extreme caution as you approach previous problem areas. Wellman leveled the Spitfire at 10,000 feet and began his cautious exploration of the speed envelope that had nearly killed him 3 weeks prior. At 300 miles per hour, the aircraft flew with the same smooth precision he recalled from the best conventional Spitfires. At 350 miles per hour, there were still no unusual vibrations or handling anomalies. As the airspeed indicator crept past 370 miles per hour, the speed at which the original system had become uncontrollable, Wellman held his breath, bracing for the violent buffeting that had forced his emergency return. Instead, the Spitfire continued to accelerate smoothly. At 400 miles per hour, the aircraft felt more stable than most fighters at half that speed. The elimination of torque reaction, combined with the resolution of vibration issues, had created something unprecedented in aviation. A powerful fighter that actually became more controllable as it approached its maximum operating range. Imagine a situation where you've worked for years on an idea many considered crazy, on a solution that went against accepted dogma. Perhaps you've faced similar skepticism, your belief in your own vision hitting a wall of misunderstanding and conventional patterns. Today, we'll tell the story of a man who not only believed, but proved that the impossible is merely what hasn't been done yet. His invention didn't just improve what existed. It overturned perceptions of what was possible in the air. In this video, we'll reveal how just one seemingly radical change can provide an advantage capable of altering the course of an entire war. And here's how it began. On that historic day, as the world held its breath and the air over Boscombe Down was thick with tension, the voice of pilot Wellman crackled over the control tower's speakers. Boscombe Control, Test 27 has reached 410 miles per hour with no adverse handling characteristics, he reported. His voice now carried genuine excitement, displacing his previous caution. The aircraft is absolutely stable and responsive. This is outstanding performance. Overseer Smith, watching from the control tower with binoculars, saw his modified Spitfire carving precise turns against the azure Hampshire sky. The contra-rotating propellers were transforming the colossal power of the Griffin engine into speed and maneuverability that seemed to defy the laws of aerodynamics. This spectacle confirmed not only months of meticulous technical work, but also his unwavering conviction that conventional approaches were insufficient for the challenges of modern warfare. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching us from. Wellman continued the tests for another 25 minutes, exploring every facet of the aircraft's operational characteristics. High-speed dives showed that the Spitfire could exceed 450 miles per hour in a controlled descent, without encountering the compressibility issues that plagued many high-performance fighters of the era. Steep turns at maximum power demonstrated handling that combined the agility of early Spitfire variants with the raw power of the Griffin engine. At 11:32 a.m., Wellman landed and taxied to the hangar, wearing the expression of a pilot who had just experienced something truly revolutionary. As he shut down the engine and climbed from the cockpit, his first words to the gathered engineers and officials carried the weight of professional experience gained over years of combat sorties. As a reminder, stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching us from. "Gentlemen," Wellman declared, removing his flight helmet and looking directly at Smith, "you haven't just created an improved Spitfire. This is the finest fighter aircraft I have ever flown. The combination of speed, handling, and control surpasses anything currently in service with any air force in the world." His words served as a verdict against all doubts and a triumph of engineering ingenuity. Air Commodore Sorley approached Smith, his expression transformed from skeptical severity to thinly veiled admiration. The successful test flight had validated not only the technical soundness of the approach, but also the strategic wisdom of pursuing unconventional solutions to seemingly intractable problems. "Mr. Smith," Sorley formally stated, "I believe congratulations are in order. Your contra-rotating propeller system has exceeded our most optimistic performance predictions." The paramount question now was how quickly production modifications could commence for operational squadrons. As the small group of engineers and officials gathered around the modified Spitfire, Smith felt the vindication of his conviction, mingled with the awareness of immense challenges ahead. Proving his system's viability was only the beginning. Translating experimental success into a battlefield advantage would require manufacturing precision, pilot training, and logistical support on a scale that would push British wartime industry to its limits. But in that moment, standing beside the aircraft that had transformed his radical idea into demonstrated reality, Smith allowed himself to envision contra-rotating Spitfires dominating the skies over Europe. Their incredible speed and maneuverability providing the superiority that could decide the outcome of the war itself. And this superiority, as we will see, was only the starting point for new technological breakthroughs that would forever change the course of aviation history.